Okay, we are going to finish the chapter 4 content. We finished lecture today talking about polar bonds. So we're going to finish talking about polar bonds in this video. And how did we define what a polar bond was? Well, on the slide we said the molecules up top, you have atoms in the bond that are identical. And because they're identical, it means that we have the same nucleus on each side and therefore the same number of protons. And they're equally pulling the electrons, okay? And we drew that over here with the chlorines. We said those electrons in the bond are being pulled equally in both directions towards both atoms. Now, the molecule down here on the bottom, HCl, because it's two different elements and we have two different nuclei, we said these electrons are not being shared equally. Now, let me clarify something. Just because you have two different atoms in a bond does not mean you have a polar bond. What makes a bond polar is when the electrons are not shared equally. So I wish I could re-highlight this, but when the electrons are not shared equally and they're pulled towards one side of the bond or towards one atom more than the other, that's what makes a bond polar. And what you end up with is one atom in the bond that we say is partial negative or electron rich, so that's chlorine. Because it's pulling the electrons towards itself. There's more protons in that nucleus. And you end up with one atom that is partial positive or electron poor because the electrons are being pulled away from it. Okay, and that is hydrogen in this case. So we said that the bonds up here, up top, these are non-polar bonds. And the bond down here between hydrogen and chlorine is a polar bond. I'm actually going to skip over this next slide because I don't really need it. What I want to get to is electronegativity. So the basis for defining something as polar versus nonpolar is this term electronegativity. And you guys may remember from like chapter 2 or 3, we introduced this term electron affinity. And we said electron affinity is basically how much an atom likes electrons and wants to gain another electron. We said the halogens have the highest electron affinity. They have 7 valence, and if they get one more, they're stable. They're like a noble gas, so they have the highest electron affinity of all the groups on the periodic table. And electron negativity is similar, but not quite the same. Electronegativity is talking about atoms within a bond, okay? Electron affinity was just talking about atoms in general. So electronegativity, we're talking about atoms within a bond, and it's how much, or let me just say, an atom's tendency to hog electrons, okay? And atoms...
Does it actually hurts our ability to relate?
Sorry, everyone. Minor interruption. An atom's tendency to hog electrons. Okay, so you know what I mean when I say hog. You tend to take more of it, draw it towards yourself, things like that. So as you go across the periodic table, what you can see, this chart is specifically an electronegativity chart. Every element on here is assigned a value, and that value is how much electronegativity it has relative to other elements. Now, if we look closely, we see fluorine has the highest. I'm going to abbreviate electronegativity. All right, fluorine does. And then down here, rubidium and potassium, they have the lowest electronegativity. So as you go across the periodic table and up towards fluorine, you increase in electronegativity. So you can judge electronegativity based on how close an element is to fluorine. The only anomaly here, the only exception is hydrogen. Hydrogen is an exception because it's not necessarily closer to fluorine than some of these metals, but it has a relatively high electronegativity because if it gains one more electron in its outer shell, it is full and more stable. So that's electronegativity. And to actually determine if a bond is polar or not, we calculate what we call an electronegativity difference. So what do we mean by this? Well, it's a measure of how polar a bond is, but how? So we're going to calculate this because, as we said, every element has a number, a sign, that represents how electronegativity is, or electronegative it is relative to other elements. So if we have a bond between any two elements, we can calculate the difference in the electronegativity of those elements. So let's look at the figures here. We have a bond between carbon and nitrogen. So if we grab those electronegativity values, they are represented down here. You take the more electronegative element, which in this case is nitrogen. We see the partial negative associated with nitrogen. It's more electronegative. It wants electrons more than carbon. It has a value of 3. Carbon is partial positive. It's the electron poor element in this bond, so the electrons are pulled towards nitrogen. Carbon has an electronegativity value of 2.5. 3 minus 2.5 gives us a value of 0.5. What does that mean? Well, hang on. We'll determine what that means in a minute. If we're looking at a bond between carbon and oxygen, oxygen is closer to fluorine, okay? Oxygen and nitrogen, closer to fluorine than carbon. So oxygen is the partial negative here. The electrons are pulled towards oxygen in this bond. Carbon is the partial positive. It's electron poor because the electrons are pulled away from carbon. The value, electronegativity value for oxygen is 3.5 minus the value for carbon, 2.5. We have a difference of 1. So if we're comparing bonds, what we're saying is that the carbon-oxygen bond is more polar, the carbon-nitrogen bond is less polar. The electrons are shared more unevenly between carbon and oxygen than between carbon and nitrogen, right? So essentially, the higher the electronegativity difference, the more polar the bond is, or a bond is, all right? Now, let's actually look at when we define something as polar versus nonpolar. This chart down here, by the way, you will have this periodic table with all these electronegativity values. I'll make a resource page for exam 2. You will have this electronegativity chart on for exam 2. You will also have this table classifying types of bonds on the resources page for exam 2. So let's look at this. En difference, electronegativity difference. If the difference between two atoms in a bond falls between 0 to 0.4, we call that bond covalent, or you might hear me call it nonpolar, or the complete term is nonpolar covalent. If the electronegativity difference is between 0.5 to 1.9, that is a polar bond. Okay, so actually both of these up here, carbon-nitrogen, carbon-oxygen bonds, these are both polar bonds, but the carbon-oxygen bond is even more polar than the carbon-nitrogen bond. So this is the actual definition for a polar bond, an electronegativity difference of 0.5 to 1.9. All right? If it's 2.0 and above, that's wildly different, right? At that point, we just call the bond ionic because we have something that's totally given away an electron, something that's totally received an electron. So it's ionic. All right. Here's just some further examples. We have a carbon-fluorine bond, a sodium chloride bond, and a bond between rubidium and fluorine. And you can see the higher the difference, 1.5, 2.1, and 3.2, if we were to classify these bonds as nonpolar, polar, or ionic, well, you just look at the table and you see, okay, does it fall? Where on this table does it fit? 1.5 is, we'd classify that as polar. And this is the electronegativity difference. It's the difference between the two atoms involved. Sodium and chlorine and rubidium and fluoride, these are both ionic. Okay, if we were classifying bonds by looking at electronegativity difference, you just look at the table. Okay, I actually had a poll. We're almost done talking about polar bonds. I wanted you to classify these particular bonds as either polar or nonpolar. So I still want you to do this. If you have a bond between iodine and chlorine, okay, that was the first one. Is this polar or nonpolar? I'm going to go ahead and write out the others, and then we'll look at these. A bond between lithium and oxygen. That was another one. A bond between bromine and bromine. And then a bond between phosphorus and bromine. All right? So we're going to calculate electronegativity difference and then classify it as nonpolar, polar, or ionic. So iodine and chlorine, these are both halogens. Iodine has an electronegativity value of 2.5. And chlorine is 3.0. So we'll do the highest minus the lowest. This number should always be positive, by the way. So always do the highest minus the lowest. So we have a difference of 0.5. This is polar. Remember, 0.5 to 1.9 is polar. All right, lithium and oxygen. Lithium is group 1. It has a value of 1. Oxygen is 3.5. So if we do 3.5 minus 1.0, that is a difference of 2.5. So this is ionic. Okay, bromine and bromine. You shouldn't even have to do the math here. If you have two identical atoms, the difference is going to be 0. So this is nonpolar. All day long. Those electrons are shared perfectly even between those two bromine atoms because the nuclei are identical. Okay, phosphorus and bromine. Phosphorus is right here, 2.1, and bromine is 2.8. So we'll do 2.8 minus 2.1, calculate the difference, 0.7, and that falls in our polar range between 0.5 and 1.9. So this is polar. All right, so that's just some examples for how to calculate electronegativity difference and whether something is polar or not. So this concludes our talk on polar bonds, and we'll pick up with polar